this is your online module on the central limit theorem. At the end of this module, you will be able to describe the central limit theorem and identify the differences between regular probability distributions and sampling distributions. Let's recall some important elements of statistical inference, starting by the fact that we do sampling to draw estimates from population parameters. You remember that you have the population and you're interested on the population parameters, but since you cannot access it all, you use samples to obtain estimates of those parameters. So we start this space for the central limit theorem from the fact that there is many potential samples that you can draw from a single population. So let's say that you have 10,000 people in your population of interest and you are drawing samples of 500, right? So there is a humongous amount of combinations that you can make of those people in subsets of 500. So let's say, for example, that you first take one sample and then from there you calculate an estimate of the population parameters from there. So you take another sample, completely different, or it might have another some elements overlapping from it. Doesn't matter. The thing is that you can estimate another set of estimates, and then you keep going and going and going until you have n different samples drawn from the same population, and you have sample estimates for that nth sample. So the core of the central limit theorem, or CLT for short, is that the sample estimates that you generate also create the distributions. And by sample estimates, what I mean is that those x bar and those s that you will calculate also generate a distribution, and in particular the mean of an estimate. So let's say and that distribution that you generate with all the estimates is also normal. And the beautiful part of this phenomenon is that the mean of that sampling distribution that you create will reach the real population mean. So basically what you do by sampling and generating estimates is that with that sampling distribution you can make stronger inferences, because then all the means will actually distribute normal. And it's the standard error of the sampling population will be equivalent to the standard deviation of the original population adjusted by the sample size. So let's say, for example, in this right panel, we have a population distribution that is a bit skewed to the right. And then this is the sample distribution, and make sure that you differentiate between sample and sampling, because the sample distribution is like, okay, so if I will take like 5 elements here and I make them drop here, where would they fall, right? So this basically represents all the 200 sample, the 200 elements that you draw from one sample. Okay, so each of those samples have 200 elements, and then you run 100 of those samples of size 200, and once you create the mean of each of them, then you take that here. So this one is for sure a normal distribution, and this is the basis of the central limit theorem, that the theoretical distribution that is described here is for sure something that we can actually use further for a future increase. So other details is that this will happen despite the original shape that your data has. So this is really powerful because it might happen with any skew distribution, any really symmetrical distribution, any type of distribution. So once you start sampling and you take the mean of those samples and create that sampling distributions, then those sampling distributions will always be normal, and that is powerful for the inquiries that we're going to make in the future. So the other thing is that the larger the size of your samples, the more you will remove skewness and kurtosis from the sampling distribution. So your sampling distribution will be better behaved if you do samples of larger size. And this makes sense in the general notion of sampling, because the closer you get to the sample, to the population size, you know, the better, right? Because you're going to have estimates that are more accurate. And the other thing is that this center limit theorem also works for any estimate that we want to draw from the population. For example, in the particular case of the mean, works in the proportion, also works. However, for when we are working with proportion, remember that we always need to make sure that observations are independent and the sample size, the original sample size, is sufficiently large. So let's check this over. Okay. So this is the tool where the link will take you. So here's the instructions of how it works. I just gonna click begin, and on the top plot you can see a regular normal distribution. You can actually change the shape here. Let's start just with a normal one, and then the sample data. In here we can animate the drawing of an actual sample, and then that sample, depending on the size, of course is usually size 5, the average of those observations will come here. And if you decide on the size of another one, let's say that we want to check the mean for a sample size of n10, we can also do so. So let's say we start by an animation, boom, 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 5, goes one sample here, 5, 6, 7, 8, 9, 10, and then goes. So I have two samples, one sample of size 5, which average came here, and then one sample of size 10, which average came here. So if I keep doing that, came here, it kept coming, 10, then I got another one. So let's say that I just run 5 of those drawings at the same time. So it gives me 5 more points in here, right? And it keeps growing. As you can see, now my mean it's really close to the original one of the distribution, which is located at 16, and the median is also closer, as well as this one, right? So the standard deviation though is different, and we will see, we will talk about why is that later. So if we run the 1,000 simulations of that, then you can see that actually the center of this sampling distribution is really, really close to the real center of the distribution, as well as the other one. So both of them are really similar, but this one is a little bit tighter. It actually has zero skewness at all. This one still has a little bit of it, and we can observe that this standard distribution is actually quite smaller than the original. So that is a tightness that is actually calculated by the square root of a standard deviation over n, which is known as the standard error. So let's see what happens with another type of distribution. So let's say we have an skew one. So let's say the same thing. We animate 5, then it goes 1, then it goes 10, it goes down. So let's animate for 5, another 5, another 5, and so on. So we have that those means actually, center in the original center of the data, and the standard deviation again will be the original standard deviation of the square root of n, which in this case is 5, and in this case is 10. So you can see how now I had a really skewed distribution, and I still had a normal sampling distribution. So let's say another type of distribution, let's say something really crazy, and this is custom, like you can actually create it. So let's say that we have this. So you see there is a lot of peaks, so this might be a multimodal distribution, or like it's really weird to actually define. but we can start animating this to say, okay, 1, 2, 3, 4, fine, boom, 1 mean, 10, boom, another mean here. We can make 5 samples, animate again, 5 goes here, a sample of 10 goes down, another 5, we animate again, and this is doing it for real. I mean, like this is a random sample generator from these data points that we gave it. So let's generate another 5, another animated, and you can see how the median, the original mean was 21.57, and it's still quite far, but let's keep going. So this is a 0.4 below. Then I keep going. If I run for 10,000 times, let's see. So now my mean goes back to what it originally was, the original distribution, and my standard deviation is what I expect to be square root of the standard deviation over square root of n. So basically, this is how the central limit theorem works. So it doesn't matter which distribution you have, how skewed or how crazy. If you start sampling and you take averages of those samples, then the distribution of those averages will be normal with certain characteristics. Like in this case, center in the same space, in the same mean where the original was, and with a standard deviation with particular characteristics. So this is something that I definitely would encourage you to practice to grasp this concept. So as a summary, in your book you have these comments actually. So basically the central limit theorem applies for both, for the proportion and for the mean. In terms of the mean, remember, so your sampling distribution will now have a mean of mu and a standard error of sigma over the square root of n. While if you are using the central limit theorem with a proportion, then the mu of that sampling distribution will be located at p, and the standard error now will be located as square root of all this over n. Okay, so it's your time to practice. This is a reminder of the learning objectives. Describe the central limit theorem, identify the differences between regular probability distributions and sampling distributions. Check your understanding through taking the quiz.